Okay. All right. Hey, I'm going to give you the simplest, the most straightforward differential equation I can think of. And that's this. The rate at which y changes as x changes is equal to y. Or in other words, the rate is equal to the output of the function. And just for giggles, let's suppose that this function starts at that point right there. What's the y value right there? Yeah, y equals 1. Zoom in on that a little bit. Okay, well this is not rocket science, folks. If the y value is 1, what's the rate of change? 1, right? They're always exactly the same. So if we were going to try to sketch this graph out, we would do something kind of like this. I'm trying to draw like a tangent or a little slope so that it looks like it's about 1, like over 1, up 1. Okay, this is not going to be perfect. But so we think the graph looks kind of like that. Now when I get right here, now the y value is 2. Well, if the y value is 2, that's going to change the rate as well, isn't it? Isn't the rate also going to be 2? So the graph would look a little something like this. Over 1, up 2. So it's getting, as the y value is getting bigger here, the graph is also getting steeper because we know the y value and the slope are the same. You guys picking up what I'm putting down so far? All right, so now we get to this point, and now that y value is 4. So that's really steep. That would be like over 1 and up 4. All right. So the upshot is that right here, the slope is constantly increasing. Now let's look at it in the other direction. I'm going to go over here. If you guys had to guess what the y value is right there, maybe we'd say something in the neighborhoods of a half. Well, that would mean that the slope is going to get smaller. And then as we're decreasing, the slope's going to get even smaller. And as we get close to 0, the slope is going to approach 0. Yeah, because the slope and the y value are all the same. Well, if as y gets close to 0, the slope is getting close to 0, that means that the graph is going to level off like this, and it's never quite going to hit that line right there. All right, now on that note, everybody, look at this function that we just drew. What does that look like that you guys have seen before? It does. It looks like exponential function. Okay, so when the rate is equal to the y value, we get an exponential function. Let's see what happens, boom, 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 if we change it just a little bit. Suppose that we say the rate of change is equal to the opposite of the y value. And let's start in the exact same spot. Let's start right there where y is 1. Okay, now we got a different game. If y is equal to 1, I plug a 1 in right here. Now the slope is going to be negative 1. So we would draw that slope kind of like this. Oh, and now you see where the game is going. Right there, it looks like the y value is 2. And so that means we would go like back 1, up 2. And now the y value is 4, so I'm going to go back 1 and up 4. And right here, as the y value is getting really small, the slope is also getting really small. So the graph is going to look kind of like that. Does this one also look exponential? Okay, so they're both exponential functions. Folks, looking for a little input from you here. What's the important distinction between these two? Between the first one and the second one? What's that big difference?
Increasing versus decreasing.
Okay, this one's increasing, this one's decreasing. I agree with that. That will always be the case. Now we have names for when an exponential function is increasing versus decreasing. Yeah. So this one's exponential growth, and this one is exponential decay. Now, what we're going to do is we're going to look at why, when the rate is proportional to the y value, you get an exponential function. So down here, let's suppose we say that the rate of change is proportional to the y value. There's a whole family of functions in which the rate at which it's changing is proportional to the y value. So I'm going to start with this. When we see rate of change, you guys know what to write. That's your dy dx. Right? This is telling me this. Is, in math, is represents equals. Now, proportional to, we don't do this in this district a whole lot in algebra, so you probably haven't seen this quite as much. But if it's proportional to y, that means if you take some constant. Now, I don't know what the constant is, so I'm going to call it k here, one of my favorite letters. It is proportional to y. So maybe there's a 1 right there, maybe there's a 10 right there, maybe there's 1,000, maybe there's a -1. But can you guys see that what I just wrote here is a variation of these two, or that's like kind of the general form. Here the k value was 1, and here the k value was -1. All right, so what we want to do is we want to take this and we want to solve the differential equation. Question so far? Okay, here we go. See that dx? You're going to multiply that to both sides. See that y? You're going to divide it. Okay, take a second on your own. I want you to rewrite this statement so that the y's are on this side, the x's are on this side. See how you're doing. You should have something like 1 over y times dy on this side. If you wrote it as dy divided by y, that's great, but it's probably easier to see what's going to happen next if you write it this way. On the other side, you've got this constant k, and it's multiplying dx. What are we wondering about so far? Okay. Keep in mind, when we're done, we want an exponential function. That's what we're gaming for here. So let's integrate both sides. Over here on the left side, we got 1 over y. Yeah. ln of the absolute value of y. On the other side, you got a k. If k was a number, give me a number. 2. If this was a 2, what would you guys say the antiderivative is? 2x. Okay, so here we're going to say kx plus. Okay, so we got it to here. we need to get that y by itself. Oh, there's a natural log sitting in front of it. So on both sides, we're going to do e raised to the power. On the left side, that's going to simplify to absolute value of y. You need to hang on to that absolute value. On the other side, some interesting stuff is going to happen. Now, remind me, gang, let's suppose you had something like this, 2 to the 3 plus 4. Couldn't you rewrite that as 2 to the 3 times 2 to the 4? That's like one of the properties that we learned like way back, 7th grade, 8th grade, something like that. You want to apply that property right here. See that addition sign? That means that you can rewrite this side as e to the kx is multiplied by e to the c. Everybody good up to there? Okay. C is a constant. What do you get when you raise that constant e to a number? You get, this is really exciting, yet another number, right? So this is some number. I don't know what it is, but I don't like writing it as e to the c. So I'm going to call that c1. This becomes c1 times e to the kx. On the other side, at the moment when you change this from e to the c to c1, that's when you can drop the absolute value. Now there's a good reason for this. There's one important difference between e to the c and c1, and that's this. E to the c must be positive, right? E to any power is a positive number. It cannot be negative, impossible. But on the other side, c1 could be negative. So at the point where you change this to c1, that's when you can drop the absolute value, because now we could have some negativity going on here. Okay, so on that note, ladies and gentlemen, look at what we have. We have our exponential function. A couple things about it. C1 right here, this has a name. This is called the initial value. Because the curve has to pass through the point when you plug 0 in, you get C1. The other thing is this, that K value. I'm going to mark that K value up top. That K value right there, whether it is positive or negative tells us something important about the function. And I'm hoping you guys can tell me. If k is positive, what do you know about the type of exponential function we're going to run into? Yep, so that's growth. And then this will be decay. Okay, so let's do one, real world example of where this kind of thing pops up. Flip the page. Poison. Now, I know you guys weren't in 6th grade in 1990 like I was, when the song Poison by Belle Biv DeVoe came out. But are we familiar with the song? That girl is poison. Cannot read that word anywhere without getting it in my head. So just know that as we're working through the rest of this problem, I'm singing that song. While you're working at the something factory, what kind of factory are we working at? The what?
Textile.
Oh, that's boring.
The unicorn.
Go crazy. Oh, the unicorn factory. Now we're talking. While you're working at the unicorn factory, slaving away to manufacture unicorns. You know, I bet you guys wondered where those unicorns come from. Yeah, they don't just make themselves. while working at the unicorn factory, you accidentally inhale some poisonous fumes. You know, it takes a lot of chemicals to make a unicorn. 20 hours later, you still feel a little woozy. So you report to the medical facility where you see Dr. You got to give me a name for the doctor. Dr. Levi it is. The good Dr. Levi measures a poison concentration in your bloodstream of this. And tells you to come back in 8 hours. And then bills you $700 for the office visit. On the second visit, your poison concentration has reduced to this. All right, now, here's the drama. Let's let T be the number of hours since your first visit to Dr. Levi, and let's let P be the poison concentration in your blood. So we've got this, and we've got this. The doctor says that the rate of change of the poison concentration varies directly with P. Back to that in a second. If at any time the poison concentration was greater than this number right here, okay, circle that, that's the death number. Is Ari jealous over there that it's not Dr. Ari?
A little bit.
Okay, if at any point it was higher than this, you will suffer permanent poison damage, which will turn you into a shirt. A bird. Okay. Okay, so this is going to be interesting because those of you that have always wanted to be a cute little bird, you're going to be hoping that the poison concentration hit that level. Everybody else, you're going to be hoping not. Will this happen? Only math can tell us. Okay, here we go. Let's start by drawing a picture of the situation. T is the number of hours since you have gone to see Dr. Levi. So here's 0. At time 0, do we know what the P, the concentration in our bloodstream, was? We do. It says at this instant it was 0.00372. And then the problem says that you come back 8 hours later. So here's 8 hours later. And at that instant, it has dropped to 0.00219. And we need to make sure that our poison concentration was never above this number right here, which is P is equal to 0.015. Okay, but here's the thing. This is not when you inhaled the dangerous fumes while making the unicorn. I assume you were working on its horn. How much time before this did you inhale the fumes?
24 hours.
Was it 24? Let's see. While
20.
working at the unicorn factory, you accidentally inhaled some fumes. 20. Okay. So can we agree that right here, 20 hours before you went and got checked out, that's when you were, I was about to say that's when you were the highest. maybe that's the case on these fumes. I don't know. That's when your concentration was the highest. Can we agree on that? So what we're interested in is what was your concentration right then? Were you above this line or were you below this line? That's going to determine whether we get turned into a bird. So here we go. Let's do the math. You guys good at least at what we're trying to find? We want to figure out what your concentration was right here. Okay, here we go. So underline this. It says the doctor, Dr. Levi, says that the rate of change of the poison concentration, would be this right here. Varies directly with P. So this is equal to K times P. We also have two conditions. We know that at time 0, this is our concentration. And we know that at time 8, this is our concentration. Okay. Using that information, we can build an equation where you can plug in a time, and it will tell you how much of the poison is in your bloodstream. So let's get it. Step number 1, separate the variables. So we would get 1 over P dP is equal to K times dt. Any questions on how I got from here to here? We good so far? All right, I want you guys to be able to do this process on your own. You can, if you don't remember all the steps, you can model it off of what we did on the last page. But I'm going to be quiet for like 2 minutes, and I'm going to let you work through this until you've got the equation. You don't need to plug anything in yet, but see if you can anti-derive and then solve for P. All right, let's see how you're doing, gang. Check your work. Do you have this? And then this? And then this? If you're not sure where any of those steps came from, please ask me now, because this is like the big idea for today. Okay, there's two quantities we need to find. We need to find C1, and we need to find K. Let's start with C1. You're going to plug in this condition. So that's the first one. And you're going to get 0.00372 is equal to C1 times e to the 0 times K. And then you're going to be like, oh, 0 times anything is 0. E to the 0 is 1. So you know that your C1 is this value. So the poison is equal to this. Now we still need K. Right? So here's where we're going to plug in our second condition. Second condition looks like so. 8, 0.00219. And I am going to continue the work right here. So that's going to give us 0.00219 is equal to 0.00372 times e to the k times 8. EK are my initials, so I get a little smirk every time I write that. All right, so now you got to be able to solve that equation. Let's do it. You want to start by getting this by itself. So you're going to divide both sides by that 0.00372. You're going to get this divided by this is equal to e to the 8k. So let me give myself just a little more space right there. All right, what's the next thing we need to do to both sides? Yeah, log this side, log this side. So you're going to get the natural log of this is equal to 8k. Therefore, k is going to be equal to 1/8 the natural log of 0.00219 over 0.00372. Grab your calculator. Okay, and I want you guys to always go at least 3 decimal places on these. The more decimal places you go, the more accurate your equation is going to be. So on this one, I would go 0.066, which means that our Poisson model is going to look like so. The Poisson is equal to 0.00372 times e to the negative 0.066 time. Okay, anything we're not sure about there? Okay, so we got it, folks. We have it. We have the equation we need. Let's come on down up here. Boom, 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 boom. Last question. Will you suffer the permanent damage of, in this case, being turned into a bird? Let's see. We want to know how much poison there was in our bloodstream at the instant that we inhaled it, and that was 20 hours before we went to see Dr. Levi. So that would be plugging negative 20 in. So I'm going to go 0.00372 times e to the, I'm going to take this whole number when I plug it in because it's the most accurate way to go, times negative 20. Okay. So our initial concentration was this 0.0140. How does that compare to the lethal? Okay, so the answer is no. No permanent damage. No bird. No bird. I had a student a handful of years ago who was really into this conspiracy theory that birds aren't real. Do you remember when that was a thing? I would say something like, but there's one out the window, and she would say, but is there? All right, ladies and gentlemen. That's it. That's the game. That's what you need to know how to do. Your for your home fun, you want to finish up problem set 2, and then problem set 3 has 2 examples similar to what we just did. One with bacteria and and the other one with buying a car. That is the game.